Okay, well, good morning, everyone. Welcome to this session of the Energy Policy Study Group. My name is Winetta Ayers. I'm the Executive Director for Commonwealth North. And we have with us today one of our co-chairs for the study group, Bernie Smith. Bernie, welcome. Did you want to say any introductory remarks? I'll handle speaker introductions for today since it's a little bit last minute and complicated, but
yeah, no problem. But I'm really excited to hear about what's going on. I heard a little bit about it last night at the QGATS board meeting, but this is really an exciting time for this new energy that's coming up here. And I'm so happy that Isaac is just jumping right in there, feet first, and getting it done. So thank you, Isaac, and the rest of the people too. Thank you.
Great. Thanks, Bernie. Well, we do have a lineup of speakers today, and I'm going to do some brief introductions if my voice holds out. Our panelists today are Isaac Vanderburg. Isaac is the CEO for Launch Alaska, and he's also a board member for Commonwealth North. And we're delighted to be partnering with Launch Alaska on this particular session. Launch Alaska has been doing a convening on green hydrogen this week, and we're happy to maybe put a little bit of a punctuation point at the end of that to bring some of the ideas and information forward for sharing with the general audience. I do want to say that Isaac, Isaac has a very impressive resume. He's involved in a lot of exciting things. In addition to Launch Alaska, he's a founding board member for Earthshot Ventures. And in his first 6 years at Launch Alaska, he's led the organization to grow more than 10 times in terms of their annual operating budget, and has expanded their portfolio to include 30 high growth climate tech startups. It's always interesting to see what entities are attracted to Launch Alaska and to exploring the idea of being engaged in the Alaska marketplace. Isaac has also managed 2 early stage investment funds. And as I mentioned, he's a founding board member for Earthshot Ventures, which is a $65 million climate tech venture capital fund. And it's the first of its kind here in Alaska. So he's engaged in the energy space in many interesting ways, including the Energy Executive Leadership Program at the National Renewable Energy Lab in Golden, Colorado, as well as the Energy Innovation and Emerging Technologies Program at Stanford. So, and I've already mentioned that he's a board member, and we're always excited to hear Isaac and the ideas that he's bringing forward in terms of the Alaska economy, the energy space in Alaska. And so welcome to Isaac. Also joining Isaac today is Erin Whitney. Erin is a research associate professor at the Alaska Center for Energy and Power at UAF. And she's the hydrogen research lead at ACEP. She has also managed the Solar Technologies Program and is a past manager of the Data Collection and Analysis Program at ACEP. She's led many projects examining renewable energy in Alaska, and particularly for Alaska communities. Before returning to Alaska, Dr. Whitney spent nearly a decade as a staff scientist at the National Renewable Energy Laboratory in Golden, Colorado. And so we welcome Erin Whitney to our program today. And joining Isaac and Erin is Peter Barnes. Peter is the Business Development Director for ZeroAvia. ZeroAvia is based in Hollister, California, and its aim is to build a zero emissions hydrogen electric aviation powertrain. This would be a fully electric propulsion system powered by hydrogen fuel cells. So they're currently a participant in Launch Alaska's tech deployment track. Again, it's an accelerator program to help move startup entities to scale their technology. So they're exploring that deployment in Alaska. And of note, ZeroAvia has signed recent deals with Ravn Alaska and the Alaska Air Group. So we welcome you all to the program today, Isaac, Erin, and Peter. Thanks for being here. So our format today, we're going to lead off with Isaac. So I'll hand it off to Isaac, and we look forward to your remarks. Thanks, Isaac.
Well, thank you, Winetta, and so exciting to, I think we've talked about, doing something together with some of the portfolio companies at Launch Alaska and Commonwealth North, and exciting that we're finally getting something on the board here. And thank you also, Bernie, for continuing your great work with this energy study group. I've had many memorable kind of conversations and made a lot of connections through this group, and it's just needed more now than ever, I think, given Alaska's energy transition that we're trying to make. And so thank you, Bernie, for keeping this group going and for inviting us to present. So I think my role, I'm going to give just kind of brief opening remarks here so that the real experts in the room can have plenty of time for their presentations, and also to leave time at the end of the session so that we can have Q&A. So I just wanted to set a little bit of context for this conversation. I think that we've known in Alaska that we have these vast, untapped renewable resources. These things have been studied for literally decades, and it's no secret that we have some of the world's largest, offshore wind, solar, geothermal, even tidal. I think the world's second or largest tidal resource just off the tip of the Port of Alaska here. But the thing that has prevented the development of those vast renewable resources historically has been that we just don't have a market for them, and they don't pencil out to for the kind of local market. And I think green hydrogen all of a sudden changes that equation in a really big way. If we think of developing those renewables, and we're talking gigawatt scale renewables, just here in this upper Cookinlet region of Alaska. If we think of converting those renewables to green hydrogen and then moving them to market through Ted Stevens International or the Port of Alaska, all of a sudden, all of those renewables are in the money. They have a market, and it's a really exciting kind of moment in time right now. And so I think that's what we're talking about here today. Is this kind of massive, and I feel once in a lifetime opportunity for Alaska to find a market for these resources that we've known about for decades. And so, yeah, I think without diving into this further for now, I think we'll get into some really interesting conversations later, hopefully in the Q&A. But I just wanted to maybe pass the mic over here to Erin Whitney, who's going to school us on green hydrogen and give us a bit of a crash course in what we're talking about with green hydrogen. So over to you, Erin.
All right, let's see if I can share successfully here. Okay, are you all seeing my screen in presentation mode?
Yes.
Great. Okay. Today, I am going to do a little bit of an intro to the scale of the hydrogen challenge, as well as some of the fundamentals and basics, which I think a lot of people lose sight of or simply need a refresher on. So we're going to jump right in. And I'm happy to be here, and it's great to be with you all virtually on a snowy day. So apologies that we can't be in person, but we'll make the most of it. Okay, let's see here. Trying to advance the slide. Okay, so the big picture here is that we need to limit global warming. This is a major finding from the latest IPCC report. If we don't curb global warming to within 1.5 degrees centigrade, we risk global consequences. And hydrogen can play a part in that. The other motivation here, if global warming doesn't tickle your fancy, is that fossil fuels are a finite resource. And we need to find, at some point, another source of energy for our Earth's activities. So pick whatever motivation suits you and gets you fired up, but hydrogen could be an answer to either of these concerns. And the drivers are really that hydrogen is a route towards decarbonizing hard to decarbonize sectors of our global greenhouse emissions. This is a plot of global greenhouse gas emissions by economic sector. And what I would like to show here is the role that hydrogen can play in each of these huge sectors. So industry, and I'm talking here about steel making, cement making, chemical manufacturing, huge use of hydrogen and huge producers of carbon dioxide. Same for transportation, huge producers of carbon dioxide. Think about planes, think about big trucks. The same in our power and heat production sectors, and also in agriculture and forestry and other land uses. Hydrogen can be used in these processes, and green hydrogen can be a way to reduce the emissions associated with a number of these processes. So we're going to dive into how all of that works. This is a little bit more of a granular view of emerging and existing demands for hydrogen. Some of the same sectors that we just saw in that pie chart. Transportation applications, again, heavy and medium duty vehicles, rail, aviation. We talked about chemical and industrial applications, power generation, and then also other types of energy systems. And I've put links here, and I can share slides afterwards so folks can go in and delve into some of the details in more depth later if they would like to. This is a sense of the scale of the hydrogen undertaking, and I should note that this slide is from 2021, I believe, July 2021, so it's over a year old, and it's probably exploded even more. But you know, we're talking about gigascale global production of hydrogen. So you can see here projects that have been announced or have been undertaken across the globe, you know, several tens of projects that are in the gigascale. You know, and keep in mind, gigascale is 10 to the 9th. So, you know, 9 zeros after that one, a billion when we're talking about watts of power. And then lots of other projects in the transportation sectors and the infrastructure projects. It really is a global undertaking, and it's hard to wrap one's mind around the absolute scale at which it's taking off. And I'll have some other numbers to help us benchmark that as we move forward. So going back to the chemical basics, when we're talking about hydrogen, we're talking about a hydrogen molecule. That's 2 hydrogen atoms. We'll also be talking about methanol, there to the right, which is carbon, 4 hydrogen atoms and an oxygen atom. Methanol we talk about because it's something that we call a hydrogen carrier. Hydrogen can be used to make methanol. Methanol can be used as a fuel, or it can be broken back down into hydrogen that can then be used as a fuel. There's some other hydrocarbon chains here for those who want to geek out on the chemistry of it. Another carrier we typically talk about is ammonia, which is a nitrogen with 3 hydrogens. That's not pictured here. But this just gives you a sense of some of the taxonomy and names of the chemicals that we're talking about. This slide has a lot of information here, and it highlights both the benefits as well as the challenges of hydrogen. So diesel and gasoline, those top 2 bars there, are great fuels in our current energy ecosystem because they have a high energy density. So if you see the big graph there, take your attention away from the inset for a moment, but the big graph there shows energy density, kilowatt hours per liter. So you can see that diesel and petrol are at the top there at 9, 10 kilowatt hours per liter. If you move down that graph, you see hydrogen, you see ammonia, you see methanol. Hydrogen at 350 bar, keep in mind 1 bar is about atmospheric pressure, so 350 bar packs some pressure, as does 700. Those are still, you know, about a 10th or a fifth as dense as those fossil fuel energy sources at the top. Ammonia, which we just mentioned as a carrier, is about a third, maybe a bit more in density than diesel and gasoline. And then methanol, it's about 50% the density of those top fuels. So by volume, at least, the energy density is not as high. But the real kicker that makes hydrogen so intriguing and so promising is its density by mass. So in that inset graph there, you can see millijoules per kilogram, or the specific energy by mass. And you can see that hydrogen is the big winner. It's several times that of the other fuels listed. Some of you may be wondering, what's the difference between the green and the blue bars? There's a latent heat of vaporization difference. It's a chemistry geek kind of thing. Don't worry about it. The main take-home message here is the high density by mass of hydrogen. So you can see 120 millijoules per kilogram there relative to natural gas, gasoline, diesel, and methanol. One of the numbers that you may hear a lot and that I use in some of my conversions, hydrogen has about 33.6 kilowatt hours per kilogram. And I like this number because we think about our electric bills in kilowatt hours, or at least those of us who look at our electric bills. Think about how many kilowatt hours you use in a month. So hydrogen has 33 of those per kilogram. Diesel, in comparison, is about, a third of that, 12 to 14 kilowatt hours per kilogram. So you can see, if you can get hydrogen in either a carrier form or a compressed form, it really packs a lot of punch. So just keep that in mind as we move forward. So again, high density by mass, but if you're trying to store it, you've got to consider these volume ramifications and the extra volumes that might be needed. So again, that summarizes the benefits and the challenges. Isaac mentioned green hydrogen. For those who don't know, when we talk about green hydrogen, we're talking about hydrogen produced from water, fueled by a renewable resource. So there's no carbon dioxide emissions. People also refer to gray hydrogen and blue hydrogen, and those are all some derivative of a fossil fuel source. So you get a CO2 emission along with other types of emissions. So again, this is how things are sort of broken out. To complicate things even more, although I will mention that the Department of Energy is moving away from the color scheme. We now talk about, mostly clean hydrogen. In the past, at least, there's been all these other colors. I can't even keep them straight. But the point is, people talk about all kinds of different colors of hydrogen. It has to do with what the source fuel is there. Today, hydrogen is produced mainly through natural gas without carbon capture, utilization, and storage. That's what CCUS means. So natural gas is used to produce that hydrogen. You can see coal is a major source of hydrogen. Very little is produced, that is green hydrogen, but that is changing. And that aqua blue, I don't know what color it's showing up on your screens there that says byproduct, that's not green hydrogen. Not actually sure what that is. Here's how hydrogen is made from these fuel sources. So the bulk of hydrogen that's produced that we just saw is from natural gas. That's the same as methane. They use steam methane reforming, and you get hydrogen and carbon dioxide out the other end. Each of these three synthesis pathways here is scaled to a product of 1,000 kilograms per hydrogen. So the output for each is 1,000 kilograms per hydrogen. So you can see the relative energy and feedstock inputs. So for example, you can see relative to steam methane reforming and methane pyrolysis, electrolysis, which is how we make green hydrogen from water, takes a lot of energy. It also takes a lot of water. Maybe not so much a concern in a place like Alaska where we have ready access to water, but this is a concern in arid regions of the world where there may be water scarcity. And again, you can see the different products here. A lot of details, but just a sense of what the energy inputs and what the outputs are when we talk about these different types of hydrogen. When we talk about electrolysis, we are using electrolyzers, and Again, a lot of details here, but there are multiple types of electrolyzers. Alkaline electrolyzers are lower cost, but there are hazards associated with liquid electrolytes, and there's ramp up times. Proton exchange membranes are getting a lot of attention these days because they're so fast, but they cost more. And there's also solid oxide electrolyzers, but they require very high temperatures. So of course, it's never simple. There's different electrolyzers out there. They have different benefits, they have different costs. I would say progress is being made on all fronts with regard to those different types. When we talk about a hydrogen ecosystem, we have a couple main chunks that make up this ecosystem. And this is a graphic that is present in a lot of Department of Energy publications. You'll see it a lot, maybe some of you already have. We just talked about production there on the left, but there's also delivery, there's storage, there's conversion into a useful fuel, and then there's the applications and what it can be used for. So I'm just going to work through each of these one by one to help you understand what the different components are and the different concerns are with each of them. So when we talk about delivery, there are different ways that this can be achieved, and obviously different geographic regions have different challenges. So, you know, trucks can deliver hydrogen. We see this already in California and Texas. Hydrogen can be liquefied. That increases its density there, and then that can be shipped or trucked. It can be transported through a pipeline, and then it can also, you know, be transported by ship. And then, as we've seen before, it has lots of different end uses. You can imagine that thinking about hydrogen delivery within Alaska, it could be a challenge. You know, we don't have an extensive road system. We don't have any hydrogen pipelines right now, but, you know, we do have ships that go in and out of our ports. So, you know, that's something we have to think about as we're thinking about how this develops in Alaska. I also want to move on to the storage piece of the hydrogen ecosystem. So the storage is interesting. You can compress it. You can turn it into a liquid. You can turn it into a carrier. On the right side there, it says material based. This is always interesting to me. This is what I first did my research on right out of graduate school at the National Renewable Energy Laboratory. I was working on chemical compounds into which you can adsorb hydrogen so that we could replace compressed hydrogen with these molecular solids that could store hydrogen. And you can think of these molecular solids sort of as Swiss cheese, you know, with lots of different holes, maybe more ordered than a Swiss cheese hunk. But these holes basically provide caverns for hydrogen. So different approaches to storage. And you can imagine with anything compressed, there are concerns there. But there are these other methods that are also being explored. And then we talk about converting hydrogen, and that's where we convert it into useful energy using combustion or fuel cells. So the basic chemistry when we're talking about making green hydrogen is you're taking hydrogen plus oxygen, and out of it you get water. And that's what is happening when we're talking about using a fuel cell. So again, you're putting in the hydrogen and oxygen, you get energy out, and then all you have is the water output. Here's another diagram that pops up in lots of Department of Energy publications showing, again, fuel cells and their sources that can go into these fuel cells. There are, you know, hydrogen fuel cells, there's ammonia fuel cells, and then again, lots of different uses that come out of this. The other thing I like to show when I'm talking about how we can use hydrogen is I like to talk a little bit about transportation. You know, electric cars are certainly catching on. Our family recently purchased one, but people are also talking about hydrogen cars. And so I often get questions about, well, you know, what's better, a hydrogen car or an electric car? You know, an electric car has a greater sort of overall efficiency, converting electricity into overall, you know, energy output, what we call tank to wheel. A hydrogen car is a little less efficient in terms of the fuel cell efficiency. And the main thinking these days is that, for short trips, so sort of passenger car applications, electric cars will prevail. But for longer haul transport, heavy duty trucks, and other transportation applications, aviation, for example, and we'll hear more about that in just a minute, hydrogen may be more promising. And that's because, when we talk about electric cars, the battery is heavy, and that's going to be prohibitive for longer transport applications. And hydrogen then starts to really shine in these longer haul transportation applications. So that's just something to think about, when we're thinking about the pros and cons of using hydrogen in transportation. This also just shows, it's, again, I promised some numbers to give, the scale of what's needed, and looking on a sort of a micro scale. If we wanted to produce, 40 kilograms of hydrogen, it takes about, 200 kilowatt hours to produce that. So, just again, to help one orient sort of the scale of what's needed and the energy that's needed to produce these outputs. So then we get to applications. This is the fun part. It's also the most overwhelming part, because hydrogen seems to be usable everywhere, and it is, which again is exciting but overwhelming. So I'm going to walk you through a diagram that is seen in a lot of Department of Energy publications again, but I think it sums it up very nicely. So we talked about how hydrogen can be used in transportation. It can be used in all these industrial applications. It can even be used to make synthetic fuels. One promising synthetic fuel is synthetic aviation fuel, or SAF. And I imagine that Peter will be talking about that in a bit. But that's where you use hydrogen and you combine it with carbon dioxide to make synthetic hydrocarbons. And that holds great promise for the aviation industry. You can think about those applications of hydrogen, and then on the other side of the diagram, let's think about the electric system. We have various sources of energy, both fossil fuel and non-fossil fuel, and hydrogen is really what can start to connect all these applications with the electric system, and it creates sort of this unified energy system, if you will. So hydrogen can be used for power generation, either combusted or used in fuel cells. Hydrogen can be integrated into the gas infrastructure. So there's talk about seeding hydrogen into natural gas supplies, even for power generation, for heating, and small amounts of hydrogen are already being seeded into natural gas supplies in pilot demonstrations for these types of applications. And then the other connection here is using electricity, and in the case of green hydrogen, using renewable electricity to generate hydrogen from water that is then used in all these applications. So this diagram can be a little overwhelming, but when you break it down into those parts, you can see all the connections and complexities and really promises of the hydrogen ecosystem. All right, so points of reference here, and this is my last slide, but I think it will help us wrap our minds around it. I did some back of the envelope calculations. The Alaska rail belt, again, that's our electric system from Fairbanks down to about Homer, has an electrical load of about 600 megawatts, which is equivalent to about 5 million megawatt hours annually, if you multiply by the number of hours in a year. And these are just ballpark estimates, plus or minus a bit. If we were to power our entire rail belt electric load with hydrogen, and this is an ideal scenario, but again, just to give you a sense, if we were to use hydrogen to meet that entire rail belt electric load, my estimate, with given fuel cell efficiencies, and again, this would be using fuel cell power, we would need over 300 million kilograms of hydrogen to meet 100% of that load. To put that in perspective, I should mention here that we have a goal from the Department of Energy to reduce a kilogram of hydrogen in cost to about $1 in 1 decade, and this will be by 2031, since it was introduced in 2021. And right now, the cost of green hydrogen is several times that, so we've got to come down here. But now to look at those volume estimates, the European Union has a target of 10 million tons of domestic renewable hydrogen production by 2030, and another 10 million tons of renewable hydrogen imports by 2030. That's the same as 10 billion kilograms. There's 1,000 kilograms in 1 metric ton. Okay, and I just said that we need, somewhere a little north of 300 million kilograms of hydrogen. So the European Union wants to import, several orders of magnitude more than that. China is the largest producer right now of hydrogen today. They produce about 33 million tons, that's 33 billion kilograms. And their demand is projected to reach 35 million tons in 2030, which would be about 5% of their Chinese energy supply, and then even more than that by 2050. So, Alaska is small in this total landscape, but what I hope this shows you is just the scale at which the world is committing to using hydrogen, and the scale to which we could see it be used in the near future. So with that, I will hand over the floor and let Peter talk about some exciting applications. So thank you so much.
Okay, Erin, thank you so much. So my name is Peter. As Juanita said, I'm with ZeroAvia. Just a couple of data points on ZeroAvia, especially in connection with Alaska. We're heavily involved with Isaac and the team on Launch Alaska, the technology cohort. So we've been working and engaging with them over the last few months, and I see Tim and Susanna, Tim Leach, Susanna Caldwell also on the lines. We've had fun working with them over the last few months, and we'll continue working with them over the next few months. And also had a great couple of days with Isaac and the team up in Girdwood, sort of talking about hydrogen subject and infrastructure, etc. So a lot of things to do, and a lot of exciting things to do. Importantly as well, our other footprint in Alaska, as I think Juanita mentioned, we have customers here as well. So we have agreements with Ravn, and we have agreements with Alaska Airlines as well. So we are pretty committed, excited to be working with Alaska, and obviously pretty committed to working with Alaska going forward. And just a couple more data points before I go into the presentation on ZeroAvia. We're, I guess, that gray area of startup to new company. We've actually been going around 4 years. We have around 200 people working with us. Our footprint, our head office is actually in Hollister, California. We do a lot of ground testing there. We have a strong footprint in the UK, in Campbell. A majority of the development work is taking place in Campbell, and I'll come on to that as I go through the presentation. And also in Seattle. Seattle is a strong footprint for us as well. A lot of electric motor development going on in Seattle. And I myself, in spite of my accent, I'm not actually part of the English part of ZeroAvia. I'm actually based in Northern Virginia. And actually, my second visit now to Alaska, love the place. So I'm sitting in my hotel room. So fortunately, we couldn't all meet in person. So I'm sitting in my hotel room and listening to these snowplows outside. So anyway, with no further ado, I'll start the presentation. So share screen. Can everyone see the presentation?
Not yet, Peter.
Oh, okay. So apologies. Just go back again. Sorry for that. Share screen. Entire screen.
There you go.
Can you see it now?
Yeah, there you go.
Perfect. I jumped forward one slide by mistake. So I think I've given an overview of ZeroAvia. So I'm going to probably take around 10 minutes or so. I've got 10 slides just to paste the presentation. And really what I'm going to walk you through is, I think I mentioned who ZeroAvia is. I think an important thing just to mention as well, some people confuse us and think we're building aircraft. We're not building aircraft. We're building the zero emission powertrains that go on those aircraft. We show a lot of pictures of aircraft because they generally look a lot more interesting than power plants. So we are the builder of and developer and builder of those zero emission power plants. So I'm going to talk you through, what is the problem actually we're tackling? And Erin actually touched on this as well. So if you remember, Erin showed, I think, transportation being around 14% of emissions today. To put that in context, the aviation industry accounts for 2.5%. So I did my math real quick. So of that 14%, aviation today accounts for around 1/5 of transportation emissions, and overall around 2.5% of greenhouse gas and other emissions. Now, the problem is with aviation, and the reason we need to do something now is aviation is growing. So even though aircraft and platforms are becoming more efficient, which is absolutely great, and SAF is part of that, the fact that the aviation industry, more aircraft are being delivered, if we don't do something today, in fact, aviation could account for around about 22% of greenhouse gas emissions by 2050. So that's pretty important. So that says to ZeroAvia that we really need to start doing something now, and that's exactly what we're doing, developing the engines to deliver that net zero solution. Now, there are various solutions. Clearly, hydrogen is important, but if we go back a couple of years with ZeroAvia, we look very carefully at what were the options open to us. So you see a lot of possible solutions out there to get to a reduced emission or zero emission solution for powering aircraft. So clearly, we're looking at hydrogen electric, but there's hydrogen combustion, there's sustainable aviation fuels, there's battery electric. I won't go into too much details in a time on this, but suffice to say, with hydrogen electric, the important thing is we're burning nothing. And I'll come on to how the fuel cell and powertrain works in a few moments. But whenever you burn anything, you get an emission, and generally it's a kind of like nasty kind of emission. So we looked at this very carefully. So hydrogen combustion, yes, it's good. It does potentially reduce emissions, but maybe only around about by 50%. When you look at sustainable aviation fuels, that's great. We see that as like an interim step and a very favorable interim step. But at the end of the day, SAF, you're probably going to get around 30, maybe 50% in terms of reduced emissions, but that's good, but it's still burning elements. There's still other emissions, nitrous oxide, sulfur, particulates, which are still being produced as part of that combustion. And I think Erin actually mentioned she did mention battery electric in the electric vehicle context. And we see a lot of battery development going on with urban mobility and short ranges. But for us, if we're looking for a powertrain that powers today's aircraft and tomorrow's aircraft where you need those ranges, battery electric doesn't really work. Partly because they are heavy, they are expensive, they're high maintenance, and they don't last an awful long period of time. And the weight of those batteries, when you start looking at the range requirements for aircraft and putting the batteries into those aircraft, the payload range capability from a passenger and payload point of view just doesn't work. So it's very, I guess, quite a simple conclusion for us. We are totally focused on hydrogen electric, and I'll come on to how that powertrain works in a moment. The solution we actually envisage, and Erin very much touched on this as well, is hopefully encapsulated in this quite simple schematic. So the world we see going forward is a world where renewables, that's the solar plant you see in the schematic there, provides the green energy to power an electrolyzer. The electrolyzer produces the hydrogen, which can be stored, and then that hydrogen is basically with a refueling truck and adapted equipment put onto the aircraft. So this picture kind of like is a schematic of how we see the world evolving and what a future kind of like success could look like. So it's a green source of energy powering electrolyzers, a solution for storage, refueling equipment, and then obviously going on board the aircraft, and obviously the aircraft will be a zero emission aircraft with our powertrains. And this looks very, very complicated. And I said, I don't want to put too many pictures of hydroelectric powertrains because they're not always that interesting or as exciting as an aircraft picture. But this schematic actually shows in a simplistic form as we can put how the powertrain actually looks. On the left-hand side, you've got a hydrogen management system. That's basically a hydrogen tank. The PGS, that's where the magic takes place. That's a fuel cell. And then the way the fuel cell works is hydrogen is introduced into the fuel cell. A chemical reaction takes place with oxygen that develops energy and heat. That energy is distributed by the next part, which is the power distribution system, into an electric motor. That's the EPS. The electric motor spins a gearbox, and drives a propeller. So that's roughly how the hydrogen electric powertrain works. And the important part on this as well is the only real emission is water. The other, I think, important element as well, we're not burning anything, and the temperatures this kind of powertrain runs at is much lower than a gas turbine. So to give an example, the early powertrains we're developing with a low temperature fuel cell are basically running around about 100 degrees centigrade. So pretty much your electric kettle at home. So that's the kind of temperatures we're working with. The next stage for us actually is going to a high temperature fuel cell, but again, it's not getting up massive magnitude in terms of increased temperatures. It's probably around about 200 degrees centigrade, which is much less than a gas turbine, which is burning, and the exhausts from a gas turbine are probably around about 600 degrees centigrade. So that's the schematic of the powertrain. So again, main points is pretty low temperature, it's zero emission, and it's not burning anything. Next part I just want to say is the story so far with ZeroAvia, where we've got to. So I mentioned we're in that kind of like gray area of startup, new company. On the left there, that's actually an early test in Hollister in 2018. The truck you actually see in the picture is, I believe, the truck owned by Val Miftakhov, our founder, where we have a rig and we're testing early electric motors, and they're actually powered by batteries. In 2019, we did our first test flight, and that was with a Piper aircraft with battery electric technology. So that's a battery powering an electric motor. That was in 2019. In 2020, this is when it starts to get very interesting. Under the High Flyer 1 project, which had some UK government funding, we flew a Piper Malibu, so 6-seater, fully powered by hydrogen and electric. So that's the first time we took off with a hydrogen powered aircraft. That's pretty exciting for us. As we move to 2021, we're starting to, we learned from those early tests. The picture you see there of the truck actually is our Hollister facility. So that's where we do a lot of the ground testing. So in 2021, what you actually see there is a development version of our ZA600 powertrain. So this is around about 600 kilowatts, and it's really targeted at the Cessna Caravan Twin Otter, if you're familiar with those aircraft, the PT-6As that power those platforms. So we start ground testing with that, or started ground testing in that in 2021. The next picture you see, which is getting even more exciting, is we have a Dornier 228. That's a 19-seater turboprop aircraft. That's based in Campbell. And we're very soon, imminently, I would say, about to test fly that aircraft. So what that aircraft has is a development version of the ZA600. So that's 600 kilowatt hydrogen electric powertrain on the left-hand side. It has the existing engine on the right-hand side. We've done high-speed tests with that aircraft, and we're very soon about to fly that aircraft. And when that aircraft flies, that'll be the largest hydrogen electric aircraft that's flown to date. And what is our roadmap going forward? So we've flown smaller aircraft, so we get a tick in the box there, that's done. We're about to flight test the Dornier 228. First commercial offering on that powertrain will be targeted for an entry into service, and I'll come on to some of the partners we're working with on that entry into service around about 2025. What we're actually doing as well, we have the next part of our roadmap is what's called a ZA2000. And that's a powertrain in the 2 to 5 megawatt class. To put that into context, that size of powertrain will be able to power 50 80-seat turboprops. So we're talking about ATRs and Dash 8s. We're spinning up that motor in the next few weeks, actually, in Hollister, and that will be attached to an adapted rig, the one you saw in the previous picture, for ground testing. And all of this ultimately is a pathway. I mean, our mission statement, probably I should have said in the beginning, is a zero emission hydrogen electric powertrain on every single aircraft. So what you see below that is our ultimate roadmap, which will be for regional aircraft, for single aisle aircraft, and ultimately long range aircraft. But you can see there over time, since 2018, we've developed the hardware, the technology. We've tested it on smaller platforms. We're already up to the 19-seat class and Cessna Caravan Twin Otter class, and we will take that in let's say robust, sensible steps in the next few years to the ADR territory, the Dash 8 territory, and ultimately single aisle territory beyond that. And I think an important part of our, let's say, a roadmap and enablers in that roadmap, and it's really the way ZeroAvia is structured. So I'm actually part of the business development team. So I'm part of the team that sells the powertrains. That's great. But it's pretty pointless selling a powertrain to a potential operator if you haven't got the infrastructure and, in fact, the regulatory side kind of like squared away as well. So what you see here is a schematic of a hydrogen refueling truck refueling a Twin Otter. So a couple of points I want to make here. In fact, number one, we have a large team actually working on the infrastructure piece of the jigsaw. Part of that team actually has been working with Isaac and the team and the Launch Alaska team. And another point I'd like to say as well is we're maturing this technology, and I'll come on to talk about some of the partners we are working with. But if I take Kemble as an example, so already today, if you walked into Kemble, so Kemble is in the UK, a very nice airfield in the countryside, in the Cotswolds in the UK, if you know the area. But if you wandered into Kemble today, you would see us putting together, in fact, what we actually have today is an electrolyzer land side. So if you're not familiar with airfields, you have a land side part and an air side part. But we have a refueling, we have an electrolyzer on the land side that's creating hydrogen, which we store at the airfield, and we've already developed prototypical refuelers to fuel the Dornier 228 you saw in the previous pictures. So that's what we have today. In fact, what we will have fairly soon at Kemble, we're putting solar panels on the hangar roofs at the airfield. So we will actually be able to produce green hydrogen, green energy, use that through the electrolyzer to produce green hydrogen to power the Dornier 228. So in fact, our test flights, which are about to start pretty soon, will be zero emission test flights. So that technology exists today in demonstrable. You can go to Kemble and you can actually see that today. But the important part for us as well is we need to work with external stakeholders, and that's airports, energy companies, equipment suppliers, etc., to make sure that when an operator who's bought our powertrains takes delivery of the aircraft, we've solved the infrastructure part of that puzzle, and the hydrogen is available for when they fly the aircraft. Just coming on, getting towards the end of the presentation now, but backers, that's incredibly important. And I already saw one of the questions in the chat about where's the funding coming from. well, we are a private company. We have significant backing and have achieved significant backing over the last few years. So to pull a few names out on the private side, we have, I mentioned Alaska Airlines. It's phenomenal to have them on board. We have Amazon, we have Microsoft through Breakthrough Energy. So these are some of our, say, private backers. And we also have funding through UK, through ATI, Department of Energy, Department of Transport, and so forth. So I think there's a message there going forward. And to answer, maybe start to answer that question that was in the chat is, I guess the question is, can this be solved by private funding alone? Possibly, but probably not. Can it be solved with private and public funding? Probably most definitely yes. Last part, where are you on partnerships? So super to have some. I'm going to split this down by customers, by airframe OEM partners, and strategic partners. On the customer side, fantastic to have Ravn and Alaska Airlines on board. That's phenomenal for us. And overall, we've got about 1,000 engines under 1,000 engines under agreement so far, which is great. And if we look at all the opportunities we see, this is worldwide going forward, we have about 2,000 potential deals in the pipeline, or engines under those deals in the pipeline going forward. So that's phenomenally encouraging for us. You see on there airlines like American and United. So these are for powertrain applications in that kind of like regional aircraft space. So that's kind of like a little bit forward in terms of our roadmap. We see on their leasing companies as well. So this is incredibly exciting for us. So what this says to us is this is a strong endorsement that we are actually doing the right thing. The airframe OEM partners, that's incredibly important for us as well. I break that probably into two areas. So what we see in the marketplace, there's a lot of clean sheet designs, which is phenomenal, looking at advanced aerodynamics, but they need a powertrain coupled with those advanced aerodynamics to really can do in that application. An example of that is, say, auto aviation with a clean sheet design. An enormously important one. I'm not putting them out just because they're more important than the rest, but I pull out Textron in that. So Textron, if you're not familiar, build the Cessna Caravan. We signed a deal with Textron a few months back, and this is basically working with Textron to retrofit the Cessna Caravan with our ZA600 hydrogen electric powertrain. That's enormously important for us, because if we want to certify that aircraft within the time frame we want and get that into service in that 2025 time frame, is enormously important for us to be working with someone like Textron. So that's absolutely phenomenal for us. And the last part, and it's very much linked to our infrastructure part, we have producers as part of our partners. We've signed deals with airports as well. Remember, that infrastructure part of the jigsaw is incredibly important. We've already signed deals with Rotterdam, Edmonton, Schiphol, etc. And there's partners as well. We develop a lot of the technology ourselves, but having, let's say, other partners brought into the ZeroAvia fold just enables us to go probably a little bit faster, a little bit more robustly. So I'd pull out High Point in that respect. So High Point are probably the world's leading producer in terms of fuel cells. And just to sort of put that into context, the ZA600 with a low temperature fuel cell and gaseous hydrogen has a robust range of around 300 nautical miles, say. But when we start to look at the next step for us, which is harnessing high temperature fuel cells with liquid hydrogen, we get the high temperature fuel cell is a little bit lighter, has a little bit more energetic punch, and with higher density energy capability with with liquid hydrogen, that enables us to sort of push it a little bit further. So really that kind of like concludes the presentation. What I would say is we're committed to Alaska, which is great. We have customers. We're having an exciting journey with Launch Alaska and the team there. We're certainly building a powertrain which can harness the hydrogen production that Erin was talking about, and putting it into an application where the operators can start to achieve their goals in terms of sustainability and reduced emissions. I didn't touch too much actually on the costs on that, but I mentioned the temperature of the hydrogen electric powertrain, but when you look at the temperature, that generally means reduced maintenance costs as well. So if you get hydrogen to the right price point and coupled with a powertrain which is running a little bit cooler, there are definitely maintenance costs and fuel cost savings that not only from an emission point of view the operator can take advantage of, but also from a cost and balance sheet point of view. So really that's it. I think that concludes my part of the presentation. So I hope that was relatively easy to understand, but I'm sure there'll be some questions.
Okay, great. Thank you so much, Peter. I'm going to add back Erin and Isaac. And I'm going to ask Bernie, did you have a question that you wanted to start with?
No, this has been an amazing presentation, and I'm so pleased to hear about it, especially on this. I guess the question to you, Peter, since you got these partners in Alaska with the airlines, when you get this thing moving, would you presume that you might have a facility, a factory here to do this, to make it a little bit simpler to get these systems on these airplanes, or would you have to do that still in your California base?
Bernie, that's a good question. I think we're still working through the precise production sites. I mean, I think we can assume that part could be in the UK and part could be on the US. Where that is in the US, that's probably still under study, I would say. So
Sure.
I guess to answer your question, have we crossed off Alaska? No. So these things are possible. We're still working through that.
All right, thank you.
Great. Thanks, Bernie. We do have a number of questions in chat. Some of them have been addressed as the presentations have gone on, but we'll kind of roll back up and take some of those. Peter, I think one of the questions, obviously in everybody's minds, is that not only do we have longer haul routes, but they're two very rural destinations, and the build out of the hydrogen infrastructure and the applicability of hydrogen on those routes is obviously going to be a concern. Just like range anxiety within a vehicle, Alaskans will have range anxiety about a hydrogen aircraft. So how do we, how do you see the development of that or the deployment of that working in a very rural setting?
That's a really good question. Okay. I think the first part of that is step by step. And in fact, we've had some great discussions over the last couple of days with Isaac and the team. So just, I think sometimes it helps with a bit of a visual, bit of a picture. So are we going to have hydrogen? And again, we mentioned Cessna Caravan. We've got a fairly good idea of the remote dispersed applications of that in Alaska. So that's great. That presents a challenge. So how do you address that challenge? Well, probably one step at a time. So I think what you could probably see is some kind of, it'd be great to see a hydrogen hub of some kind in Alaska. Remember, Ravn are one of our customers operating out of Anchorage. So that kind of makes sense. That kind of like connects with there. So you could see hydrogen there. As Erin, I think Erin mentioned as well, you can transport hydrogen. There's a rail link up to like Fairbanks. That's maybe possibly, I'm just trying to paint a bit of a picture here. That's possibly a second step. And then the question, in fact, what I didn't say on the infrastructure side is you have choices how you get that hydrogen to an aircraft. And those choices are, is it produced on site? Because if you have a power source and a water source and an electrolyzer, you can produce hydrogen. So it's not beyond the realms of possibility. You have micro hubs of hydrogen production to fuel those aircraft, or does it make sense to have a larger hub and you transport those by rail, truck, or pipeline to other hubs? So what I'd say is, I think the answer to that is we understand the issue, and there is probably more than one possible solution to it, some of which I've talked around then. And the way you would approach it is step by step, and probably, possibly starting with a hub around the Anchorage, Cook Inlet area. So I'm not sure if that helps.
That's great, thank you. I guess just to add on to that, and I see Barbara Haney has added a question here about temperature sensitivity for the powertrains, and does that degrade range or other operational aspects of the aircraft? What I would say is that, in Alaska, obviously the build out of our transportation system is still relatively primitive. And we do have another question about for longer haul question. So I maybe answer the temperature sensitivity question, and then I think it was Ben, Alan Bailey was asking about longer haul flights and accommodating hydrogen fuel tanks. One of our, I actually was going to start with this. Aviation is very much a part of our identity as Alaskans. Most children in Alaska have flown before they've ever been on most other forms of transportation. So, being an innovator in this space is probably not, really not that unusual for Alaska, but
Sure.
how the build out of the hydrogen infrastructure would work, and how it would be accommodated given our environment and the safety concerns of our big geography and extreme conditions. How do you address that?
Yeah, Juanetta, I think I've kind of presented a picture in terms of how it could possibly roll out step by step. I think there's two questions in there, correct if I'm wrong. One was about temperature, and Alaska is pretty extreme in that respect. The other one I think was around hydrogen storage on aircraft. So shall I break it down into those two? Yeah, I mean, the temperature one's a great one. Temperature one is a great one. Well, number one, the aircraft has to be certified. So as our flight test and certification process, the temperature question will be addressed. We don't foresee any issues with that, so it will go through that process and get certified and flush out if there are. We don't foresee any if there are any temperature issues with that. The other one, not being flippant, and I think Alaska is a great example. If it works in Alaska, it will work anywhere. so but that will be clearly like after certification. And on the hydrogen storage, that's a really good one as well. As Erin said, I think hydrogen from an energy density point of view per kilo is phenomenal. I think the hydrogen is, and again, Erin or other people, please correct me on this, but if you look at hydrogen versus, say, lithium-ion batteries as an example, it's like 100 times better in terms of energy per kilo than a lithium-ion battery. And everyone thinks a lithium-ion battery is great, which they are. The other one I would say, if you actually take a kilo of kerosene, and Erin, I was looking at your charts as well, just to check my math was correct, and I think it was those blue and the yellow lines. But I think if you take a kilo of kerosene and a kilo by weight of hydrogen, it's about 5 times more energy efficient. You get 5 times more energy from hydrogen, so it's phenomenal. The only downside, and I think Erin showed that in our charts, it's kind of not particularly dense, so you need larger containers to store that, which is okay from a weight point of view, but not always from a volume point of view on an aircraft. So what we see, I'll take Cessna Caravan as an example. We are looking, without going into too much detail, we're looking at innovative ways, and I mentioned gaseous can be foreseen on the Caravan to start. We don't want to put it in the passenger cabin, probably not a great idea, but Caravan, potentially, you see some of our photographs of the Caravan schematics, and you'll see wing tanks. There's a belly pod there to put hydrogen. So there's innovative ways to actually get that hydrogen on board the aircraft. When we look at, and then the next step, I think, when we go to and we show our schematics of ATRs, you know, the 50, 80 seat aircraft and the Q400s, by that stage, we'll be looking at liquid hydrogen. So the challenge of finding space becomes less problematic, and we have time to find that space on the aircraft. Could it be on the cabin? Absolutely. Could it be can you utilize other areas? And there's an area we're looking at, and I didn't have time to go into it in too much detail in this presentation, but there are ways to do, we're looking at conformal tank technology. So I'm ex-Airbus actually, and I've had it, without going into too much detail, I've had a lot of experience trying to squeeze how you can use space on an aircraft that you didn't think you could use before. And it's things like fairings and that type of thing. So where I'm going with that is we have enough time, and potentially and possibly with conformal tank technology, of finding the right amount of space on board the platform with liquid hydrogen to get the hydrogen on board. So is it a challenge? Yes, it is. Is it insurmountable? I don't think so, but it needs a bit of creativity.
Well, we've talked a little bit today about what it would take to do build out the infrastructure, and I see some questions popping in, but I'm gonna put this one in there. Peter, your schematic showed your energy source coming from solar, and we have other potential energy sources that could play a role in the hydrogen build out in Alaska. And just wondering, Erin, do you want to touch on maybe geothermal or other potential renewable sources for that might be part of a hydrogen regime in the future?
Yeah, it depends on the scale that we're talking. You know, for domestic use, you know, we don't need as much as perhaps, say, for export potential. And there's been a lot of talk about using the export potential of hydrogen to marketize a lot of our stranded resources here in the state. So you mentioned geothermal. Yes, we have geothermal prospects, you know, across the inlet there, Mount Spur, et cetera. Some of those are being actively explored and developed. You know, the other key resources that we have in this state are tidal resources, especially in Cook Inlet. You know, we have the second biggest tides in the world, and there's active research right now on harnessing those tidal resources, both for our domestic use as well as to potentially produce exportable goods like hydrogen. The other promising one is wind, and not just landlocked wind, but offshore wind. That is an active area of inquiry and potential development also. in the Cook Inlet region. And, we're talking gigawatt scale energy generation here. And that's what's going to be needed to make hydrogen at any kind of scale, to make it economical, not only for export, but in turn and by consequence for our use as well. So I think tidal and wind are big, very promising resources for Alaska. Geothermal, of course. Solar, yes, maybe on a smaller scale. And of course, we don't have a year-round solar resource up here, at least at a consistent intensity. So those are some of the resources that I can point to as quite promising in terms of green hydrogen. And I should mention, although it may not be of interest or as much interest to this group, there's lots of talk about a gas pipeline and what that might mean for making hydrogen if combined with carbon capture, utilization, and storage. So again, bringing natural gas down from the North Slope, converting it to hydrogen using the Agrium plant to make ammonia, combining that with carbon capture to make a cleaner version of that hydrogen and in quantities that are exportable. So I hope that answers your question.
So it makes more sense to transport the natural gas off the slope and do the conversion in South Central, as opposed to what are there greater efficiencies to be achieved by doing conversion earlier in the process? Or
well, I think the bigger question is, how do you transport it once you convert it? Mm-hmm. So if it's converted on the North Slope, it's got to be transported from the North Slope. And that's a good question. Should it be converted and then transported from there? I think, one of the attractions of converting it down here, and I'm certainly not speaking for the project by any means, is that we have this Agrium plant that has already operated. So it's already here. And it's ready to be turned on with a bit of refurbishment. So the infrastructure is already there. There are other efforts certainly underway to think about how to convert natural gas to carrier fuels on the North Slope. And I think we'll all be hearing more about some of those specifics in the coming months and years.
Great, thank you. Sean Scaling with Chugach Electric is online, and he's asking about what's the estimated future market value of green hydrogen, and will it track with the value of natural gas? I know, Isaac, you've provided a resource here, but do you want to address that?
Yeah, I think I posted just one data point, which is one group that is estimating the market growth for green hydrogen. Is that what you're getting after, Sean, or are you asking more about price? Or
I think it's more, is it price or energy generation, Sean?
Value.
I can jump in actually and just say that I can't do the calculation quick enough to get back to you right now, Sean, but I know how to reach you. The way to do this is to think about the current price of hydrogen and think about what the BTU content of hydrogen is. And then if you know what the BTU content of natural gas is, then you can at least compare the same BTU amounts and the price projections there. So let me work on that for you and get back to you. I think we're both interested.
I just want to roll up here and see. Missed all the questions. Picked up all the questions, sorry. Well, I'll roll back up to this earlier question from Ann Donnelly about the cost. Now, some of that has been addressed, but in terms of the build out of hydrogen infrastructure to be able to accommodate all the applications, the potential applications. And I'll just note also that Barbara and Erin were conversing about the use of hydrogen for heavy truckloads for a mining application, and Erin provided a reference for that. But obviously, the build out of this hydrogen infrastructure is going to be quite costly. Any kind of energy regime transition is going to be quite costly. But how do you see those investments rolling out? What are the critical pieces? What creates the tipping point towards a hydrogen-based economy?
Are you asking me?
Any of you?
Well, I think you have to have the demand first, or the projected demand. And those pieces that I outlined, you've got production, you've got storage and delivery, and you've got conversion. And I think we have to think about what role Alaska wants to play. Are we the producers? Are we the transporters? I think we could very well be the producers. And we probably then have to also be the distributors too, or at least get it to a point where someone else takes off. But we're also the users. I know that's maybe seems like a cop-out of an answer. I'm not sure. It's sort of a chicken and egg problem, but somebody else might want to take a crack at that.
Yeah, well, I'll say a couple of things that I think I touched on it during the presentation. So here we go. This is off the top of my head. I think how I see this is from an aviation perspective, and the perspective that ZeroAvia is in at the moment. So there's a small hump. So we know the future. So we know hydrogen presents enormous advantages and potential in terms of environmental reduction and impact. It's fantastic. Now, history will show that when you kind of have to go for something, there's an environmental benefit, there's a cost associated with that in terms of operating costs. But in fact, I think I mentioned during the presentation, when you look at the energy density of hydrogen and the potential cost of that, coupled with the low temperatures and the low maintenance costs, the actual operating costs are low, and the environmental impact is incredibly positive. So that's kind of like where you need to get to. But we know there's a small hump, and that hump is like the transition cost. So it's from an operator perspective, they've transitioned their fleet, and we in the deals we strike, we can justify the economics of that. There's a conversion cost. But you mentioned like the infrastructure, and I think it's like no one size fits all. So from our experience, and I mentioned we are involved in certain of the hydrogen hubs that are being developed in the US. We're certainly involved in terms of the build out of the airport infrastructure. And there's no single formula or framework that applies to all of those. It's different. And I think that comes down to the funding. So, and I think I mentioned that. So part of it, could it be done with just private funding alone, knowing that there's a very good world to get to, possibly? Can it be done with a mixture of like state, federal incentives, funding, grants? Absolutely. I think that's probably the outcome that will take place. And we see that in the projects that we're involved in. So I won't get into the details of those, but whether it's Edmonton, whether it's the hubs we're looking at, whether it's Schiphol or Rotterdam, that's the kind of like pattern we see, that kind of like partnership with the stakeholders there. They know where we need to get to, and it's a very good world from a cost and environmental impact point of view. It's not without cost in terms of getting over that hump transition. How's that funded? Well, that's kind of like the work we get into when we look at those hubs. So there is a cost, but it's probably a mixture of private and federal and state. Yeah.
And Isaac, did you have anything on that you wanted to jump in on?
No, I mean, it was an interesting kind of thought exercise this last 2 days in Girdwood, where we were, looking 15 years out and focusing on, taking the idea of green hydrogen for a walk. And, to Erin's point, if we just focused on the potential use of hydrogen at Ted Stevens over the next 15 or 20 years, and then also think about maybe some seasonal storage for the railbelt utilities, and then some hydrogen for maritime and shipping. The amount of renewables that we would need to build in the next 15 or 20 years is, this is a real swag, but somewhere in the order of 50 gigawatts of renewables, which is many orders of magnitude larger than what we have, as a total load in Alaska at the moment. So this is a big number. My colleague Rob Roy's, ran another interesting number just kind of back of the napkin recently, and if you look at the BTU energy potential from renewable resources in this region alone, the upper in the region of Alaska, there's more kind of energy potential in this region, for production in 2 years than we've seen on the entire North Slope of Alaska since the 1960s or 70s. Like, it is a massive energy resource, and if we're going to develop that, it's an extremely big project. Certainly the biggest kind of project I've seen in my 20 years of kind of looking at this stuff. So that's part of the equation here. It's just like developing those renewables, and I think a lot of the business model for developing renewables is really private sector led, with counting on some of those kind of different rebates and incentives and tax incentives and ITC, PTC tax credits that are out there. So that's just one part of this. Just one part of this is just the generation.
So we've got a couple more questions. With your indulgence, we'll just kind of maybe try and walk through those. But this question is for Erin. I know that the old MMS had a scenario for geothermal hydrogen production with storage in silica structures, underground silica structures on the Alaska Peninsula. I don't know if you're familiar with that or not, but storage being one of the major issues with the transition to hydrogen, do you see that as something that might be viable in the future?
We are actively discussing that and talking about it. We store natural gas in caverns, underground. And so the question is, are those suitable for hydrogen? The tricky thing about hydrogen is that it's a super, super small molecule. If anyone does leak detection, on equipment, you use helium, which is about the same size as hydrogen. And you use helium because it can slip through the little leaks really quickly, and then you put soap on it and you look for the bubbles, right? So hydrogen can get out of just about anything. So that's the big trick. Another question is, what if you converted hydrogen to a carrier that would be easier to store, because it would be bigger. But then again, you have that additional cost and infrastructure associated with conversion. So I think the jury is still out, at least in my mind. There are others who may hold more definitive views on that, but that is a big question. And you've hit the nail on the head in terms of where all the current conversations are.
So we do have some other questions. I'm going to try and encapsulate a couple of these, but so one of the questions is always, this issue of transitioning from one energy regime to another. And Anne Donnelly is online with us, and she's asking, are we sending mixed messages as a state in terms of the oil and gas industry and investing in oil and gas versus investing in conversion to another energy regime, in this case, hydro. She concludes with the question, is there enough natural gas during the transition for Alaska's winter demand? Well, the utilities are already talking about importing natural gas. So the answer is maybe not without some additional development in natural gas. So Erin, you want to speak to that?
Yeah, well, again, another hot topic of conversation currently. The more we can chip into our natural gas usage, the more we can prolong the life of our natural gas supplies down here in Cook Inlet that we do depend so heavily on for our power. There will be a transition period. I don't think we're sending a message not to invest to oil and gas developers, because I think that, for example, the Alaska Gas Line Development Corporation just led a hydrogen hubs proposal to the Department of Energy that went in early November. And, the premise of that proposal is that, a gas pipeline from the North Slope. And I realize that's not cook inlet gas, but just to give you a sense of what some of the oil and gas developers are thinking, is that gas pipeline could help jumpstart a larger hydrogen economy that would eventually transition to green hydrogen, because there's money in oil and gas, whether you like it or not, there's money in it. And it's a great way to get infrastructure in the ground. And that, the gas pipeline is envisioned as a feedstock for ammonia production, again, combined with carbon capture, that could bring clean hydrogen that would then satisfy these burgeoning Asian demands and global demands for green hydrogen or clean hydrogen. And the thought is, that once you start that process, renewables will kick in and scale up to the degree that's needed and can use that infrastructure that's been established by the gas developers. That's one route. I'm not saying that's the only route, but I actually think that they can be complementary. They could coexist. It's anyone's guess how this is all going to develop. I realize the gas line's a very, topic that brings out lots of strong opinions, but I'm simply presenting sort of how people are thinking about it.
Great, thanks. And anybody else, if you want to, Peter or Isaac, if you want to weigh in on that, go ahead, Peter.
Sure, Vanessa. Yeah, I'm not an infrastructure expert, but clearly Alaska has oil and gas. It's, as Erin pointed out, it's like a finite resource. So if we're talking about a transition, you don't wait until that runs out and then start, okay, what do we need next? So I'd portray it as it's a finite resource. Okay, there's export opportunities today. That kind of like determines your transition time. There's, of course, you can go faster, which I think is beneficial, but it kind of like bookends how slow that transition could be, if you like. I'm not sure if that makes sense, but it's going to run out at some time. You need an alternative. The alternative most likely is hydrogen, and that transition can take place over that period of time. So,
Isaac?
Yeah, and I think that it is a hot topic, but there's also like pretty broad consensus that, even in the AGDC hydrogen hub proposal, there's a transition to green over time, and so I view these efforts as extremely complementary. We see a real opportunity for investment in this region to build out the green hydrogen hub. I see this as a major economic, project potential for the state, and we should take a hard run at it, and then also find other solutions for the short term to make sure that we can keep the lights on and folks' homes heated until we make this transition. But I view it all as super complementary, and we need to, more than ever in Alaska, we need to be thinking big and moving quickly, and we're all in full sprint mode to figure out what's next year. So it's all part of the same effort, I feel.
That's great. Thank you. Thanks, Isaac. Hey, I know you guys have other meetings to get to today. I'm going to close the question and answer there. My apologies to anybody who I didn't get to specifically. I hope that your questions were answered at least tangentially by some of the other questions and answers. I think the good news for Alaska is we have an embarrassment of riches both with existing energy regimes and the potential for new ones. And we also have the energy that can be the transition, part of the transition economy to get to whatever those new energy regimes may be. Bernie, any closing thoughts from you?
I just think this is a great opportunity for Alaska. Hydrogen is just on the map right now. It's incredible that down in West Texas, they're just putting $4 billion into a new hydrogen plant, green hydrogen plant that is fully powered by renewables, which is even more amazing. More than a gigawatt of renewables for a $4 billion plant. So it's out there, and I'm just real pleased that Isaac and his group and Erin and her group are just, looking at all the different items that could be done. So thank you to all three of you.
Great. Thank you. Thank you, Bernie. Thank you, Isaac. Thank you, Peter. Thank you, Erin. We appreciate your time. And thanks to everybody online for being with us today. Again, we will post the recording of today's session along with the speaker slide deck, and you'll be noticed when those are available for viewing. So thanks again, everybody. Stay safe, stay off the roads if you can, and happy holidays to everyone. Thanks so much.
Okay,
Thanks all.
thank you so much.